this conference for us. And I want to talk about random generation of finite simple groups. Basically some of the main results and also some of the methods that people use when they're studying these things. Okay, so let's start with the group G. And in a moment I'm going to make it finite, but right now it'll just be a group. And we're going to define the generating graph. The generating graph will be gamma of G, and it's going to have vertices. The group without the identity, and as edges, there's going to be an edge between two elements x and y whenever those two elements generate the whole group. Okay. So now let's make G finite. When G is finite, it's easy for me to define this probability. It's going to be the probability that two random elements generate G. Okay, so another way of writing this in terms of the graph is it's the number of edges in the graph divided by the number of pairs in G. Okay, so because it's finite, this is all easy to define. I don't have to worry about infinities. Okay, so first I want to mention this famous result of Steinberg. So probably you already know this. If G is a finite simple group, then there are two generators. So there exist x and y, such that x and y generate the group. Another way of saying this in the language that we have just defined is that this graph has an edge. Okay, so it makes sense to study this graph because it's not just empty. And another way to say it is, this is kind of sneaky, but the probability that two elements generate G is positive. Okay, so a natural question might be, what is this probability? And so that's what we're going to be asking ourselves. Wait, this was 62. This next result was in 1969. And Dixon studied the alternating groups. Okay, so he showed that the probability that two random elements generate the alternating group in the limit as n grows is 1. What this means in terms of the graph is that almost all of the edges that can be there are actually there. So I want to give a brief idea of how this was proved. The proof here, we're not going to use any Onan-Scott, we're not going to use any maximal subgroups. We're just going to use statistics about random permutations. So, okay, I'm going to be writing G all the time, so G is going to be AN. And if we define Pn to be the proportion of pairs which generate a primitive group, in the natural action on our endpoints. Then, okay, Dixon shows that this is roughly 1 minus 1 over n, and then we have lower order terms. So So in particular, this tends to 1 as n grows. And the methods that are used here are just statistics of random permutations. Right, we just want to check that we're transitive and we don't fix some partition. And then we need a second kind of lemma to help us with the proof. And this is quite a famous lemma. So if I have a primitive permutation group, and I contain a certain kind of element, what happened? There we go, okay. If I have a primitive permutation group and I contain a Q cycle, where Q is some prime that's small enough, and by small enough, it doesn't have to be very small. So if I know I'm primitive and I contain this Q cycle, then, H has to be alternating or symmetric. So what I'm going to do is I'm going to say, okay, I'm picking 2 random elements in my group, then with high probability, this probability, they generate something which is primitive. So now I basically have a primitive group H. So now I would like to look for a Q cycle in my group H, and then I'll know it's AN or SN. It's already in AN, so it's AN. That's the idea. So now what we need to do is look at statistics of permutations that have a Q cycle like this. And to do that, we're going to first look at this different set of elements. Elements that have exactly 1 Q cycle. And then all the other cycles are co-prime. And this is where Q is some prime, and Q is in most n-3. Okay, so you can estimate the size of this group just by looking at cycle types of random permutations. And so Dixon showed that if we let little q be the proportion of elements contained here, then it's going to be basically going to 1 as n goes to infinity. Did I make a mistake? Okay.
No, we were just wondering, this is just a set, but you wrote it as a set, so it's fine.
This is just a set, yes. Yeah. Okay. So again, this is using statistics of random permutations, just looking at their cycle types. Okay, but this set here is not quite what we wanted, right? We need Q cycles. We have Q cycles with other stuff attached. So what you do is, because the other cycles are co-prime, you just take a power to annihilate them. And then, so I guess we can write, if you have an element in Qn, then I guess G to the K is a Q cycle for some power K. Just make it so that it annihilates one of our co-prime cycles. Okay, so let's do a brief recap. We want to show that the probability that 2 random elements generate tends to 1. We know that with high probability, our 2 random elements generate something primitive. And we know that if a primitive group contains a Q cycle, then it's going to be the whole group. And then we also know that with probability tending to 1, our group does contain a Q cycle. So now we're done. So, okay, the probability that let's pick two random elements, right? So x and y be uniform in G. So we're going to pick two dependent elements. And the probability that the alternating group is contained in the group generated by them, well, it's at least the probability that our generated group is primitive, and let's say x is in Qn. Okay, you will notice that these two events here are probably not independent. However, they're both almost everything, so their intersection is also almost everything. So this tends to 1 as n goes to infinity. Okay, so all of this, now we've proved our result. All of this is not relying on Onam-Scott, is not relying on any knowledge about the structure of subgroups in AN. It just relies on knowing things about the cycle types of random permutations. So this is classification of finite simple group free. And we're just doing statistics of random permutations. Okay. So the next natural question is, can we replace AN by, just a finite simple group? And the answer is yes. So we had to wait a little bit longer to get this, because in 95, Liebeck and Shalev proved the analogous result. So let's have G to be a finite simple group. Then the probability that two random elements generate G tends to 1, and now in our limit we need the size of G grows. So again, in this case, it means that the generating graph has almost all of the possible edges that it could have. So now we're going to need the classification. And we're going to look at the non-abelian groups. We have our three classes. Okay. This case is being done by Dixon. We just saw that. In this case, we actually sneakily don't need to do anything because there's only finitely many. We don't even care how many, because we're taking the limit as the group size grows. And so we'll just assume that all of the groups we're looking at have order greater than that of n sporadic. So we don't need to do anything here, pretty sweet. And so now we just have the groups of Lie type left. And in the groups of Lie type, you're going to have things like, PSL, and also, our exceptional groups. If we want to make these things grow, then we're going to need to take either Q goes to infinity or n goes to infinity. Right, so we need to be thinking about writing down our probability in terms of Q and n, and then checking that this goes to 1 if Q goes to infinity or n goes to infinity. It's the basic idea. And the way that we're going to tackle this is by using more classification stuff, which is our knowledge of the maximal subgroups. Okay, so why are maximal subgroups interesting here? Well, if we have a pair that doesn't generate the group, then they must generate some subgroup, and that subgroup is contained in some maximal subgroup. Therefore, we get that there exists a maximal subgroup which contains both G and H, and it's the same the other way around, of course. So we can write down our probability, or I guess 1 minus our probability, right? Because this is a way of understanding when G and H do not generate. Okay, so this is going to be bounded by the number of pairs in M divided by the number of pairs in G, big square here, and we are going to be summing over all of the maximal subgroups of G. And then we know lots of things about conjugacy classes of maximal subgroups, so let's kind of move to that picture. So this is the same as, let's call R a representative of a conjugacy class of maximal subgroups. And yeah, so we're going to need this quantity, and then we need the number of elements in the conjugacy class, which is going to be this thing with the normalizer. But we know that the normalizer contains R, and so we actually get this really cute bound. You just need to know R over G whenever R is one of those representatives.
One over the normalizer. That's
Because
oh, yeah, sorry.
yeah, so sorry, this is an inequality explicitly. But it turns out that this step
Square there, yeah,
is
okay.
fine. Yeah. Okay, so what do we actually want to show? Well, we have a bound on this, and we want this to go to 1, so we want the whole thing to go to 0. So we would like to want to show that this goes to 0 as n goes to infinity or q goes to infinity.
Excuse me, why is this not equality? Because the normalizer is actually equal to R, right? Shouldn't it even be equality?
The final step is equality because the normalizer is on.
Fair enough. I think this step may also be
That's inequality because you're doing inclusion exclusion
yes.
badly.
Okay, yeah, thank you. Okay, so now let's look at our classification of maximal subgroups. Let's do the example for the special linear case. So this case was actually done by Cantor and Lebotsky in 1990. So Liebach and Shalev finished up most of the exceptional groups, but Cantor and Lebotsky did a lot of the other groups. Okay, so this is all going to be very rough. We're going to look at roughly what the subgroup structure is, and then we're going to look at roughly the number of conjugacy classes. And let's not do all of the types, but let's do a little table and kind of, you know, something like that. So, okay, C1, we've got the parabolics. And there's some linear number, I'm going to say 2n, of conjugacy classes here. And then for C2, we're going to have our groups that look, you know, they fix a direct sum. So it's going to be something like this. And this is for t dividing n. So there's one class for each t. So how many classes are there? The number of divisors of n. And we can bound that above, bound that above by n. You know, something like that. And we can keep going. So here, for C3, these are the extension field ones. So we have one for each prime, which divides n. Number of prime divisors is still less than or equal to n. C4, again, same game. For C5, these are our subfield stabilizers. And so these look something like this. If you'll excuse the notation. So, okay, how many are we going to have here? We can bound this above by log q. And then we just keep going, do all of them. I may as well write them out. C6, there's only one of them. C7, there's around log n of them. And C8, there are 4 of them. Okay, and in all of these cases, So if M is one of these maximal subgroups, then we have some bound on the index. So we're just going to stick these two things together to get the contribution to our sum of all of the representatives from C1 to C8. Okay, so this is not the full sum, but it's almost everything. And this is the sum we wanted to look at. So we can estimate this by, I guess, 2 over this thing times, okay, let's take a look. We've got 5n plus 5 plus log n plus log q. Okay, we want this to go to 0. Does it go to 0? Yeah. So it goes to 0 as n goes to infinity. Oops. It also goes to 0 as q goes to infinity. So we're good here. What's left to do is the class S. It's basically the same game, but it's slightly less pretty to write down. So I'm just going to write that as similar. Okay. So this is the end of our proof. And yeah, so one more thing I want to mention about this is that we now know that the probability tends to 1. And we know that the probability is always positive in every individual case. So the next question might be, is there some universal bound that bounds it away from 0? Or does it somehow go to 0 if you're, can you get something that gets progressively smaller? So this is a much more recent result of Menezes, Quick, and Rodriguez. And they gave a lower bound. So, okay, I guess I should say, let's take a finite sample group G. And they showed that the probability that 2 random elements generate the group is bounded below by 53 over 90, which in particular is greater than a half. So if you're looking at the graph, you have more than half of the edges. So it's pretty good. And I guess we have equality in our first inequality, if and only if we're in the case of the alternating group. So the bound is attained. Okay, and the methods for this, they're the same methods as, they're the same methods as what we just discussed, but they're just really, really careful about checking all of the specific numbers. So we obviously our bound was like wildly too big, right? It was still 0. So they just went through and actually checked everything, and they found this bound. Okay, so now I want to shift gears a little bit. I'm still going to be talking about random generation, but I'm going to be talking about a different problem, which I'm going to advertise as having some computational Galois theory motivation. Okay, so we're going to need just a couple of definitions, and then we'll get to the Galois theory. The subgroup of G, which is invariably generated by some subset G1 through GK. We're going to denote it by, it's going to look like the set generated by G1 to GK, and the sub I, and it's going to be, okay, we're going to take an intersection of groups generated by things, and those things will be conjugates of each of my G's. Okay. Here we go. And I'm going to take the intersection over all possible tuples in G. Okay, this looks weird. What really is it? It's basically, it's the group that you can guarantee that these guys generate if you're allowed to swap any of them by any of their conjugates. So let's say I give you some elements in a group, but I actually only give you the information about what the conjugacy classes are. I don't give you the information about what the specific element is. What group can you guarantee you generate? It's going to be this group. You need to take the intersection over all ways of conjugating everything in every possible way. So let's just see a couple of examples. So we know that this set here generates S4. What about if I try invariably generating from this set? Well, it's going to be contained in, and now I'm just going to write whatever conjugates of these things I want. So I can just put a different transposition. Right, and this group is not the whole of S4. So this, this pair doesn't invariably generate S4, but it does generate it. And there is a result which was kind of published by two different groups of people at the same time, so I'm going to be writing a lot of names. And this was in the 2010s. They showed that, so this is basically the equivalent of the Steinberg result from the very beginning. They showed that there exists, oh sorry, we should assume that G is a finite simple group. Then there exists a pair which invariably generates So that's nice. That means that we can basically ask all the same questions that we were asking before, but with the word invariably in there instead. However, there's one very weird consequence, which is that in general, a group generates itself, even if it's infinite or whatever. This is no longer true for invariable generation. So this is just kind of a cute example, which is that, okay, let's take SLN C. Because I can upper triangularize each of these things, this is going to be contained in the group of upper triangular matrices. Sorry?
Variable.
Yep. There we go. Okay, because I can conjugate each of them into an upper triangular matrix, I'm not going to be able to generate, the group generates itself, but it doesn't invariably generate itself. Okay, so this is kind of fun, and also there's actually some very simple things, seemingly simple things that are not known. For example, we don't even know if this is, it's not known whether SLNQ invariably generates itself. So there's some very weird examples when we're in infinite groups, but with finite simple groups, everything is as we would expect. Okay, so I promised some Galois theory. Let's have a polynomial. So we're going to have a polynomial with integer coefficients of degree n. When I write this sub n, it means degree n. And we want to look at its Galois group over Q, say. And we know that this is a subgroup of Sn. The question is, which subgroup of Sn is it? So what we're going to do in a minute is try to write some algorithm that takes a given polynomial like this and tells you whether or not the Galois group is Sn. But first we need to notice something, which is that, okay, if you take a prime, because all of these coefficients are in Z, we're able to look at them modulo p. And so then you get a new polynomial modulo p, and you can factorize it and look at the degrees of the irreducible factors. The sum of those degrees will be n, and so what you've actually done is get a partition of n. So I'm going to say the degrees of irreducible factors of F modulo P, they form a partition. And we're going to call it lambda P. And now we're going to look at the Frobenius density theorem and see what it tells us about lambda P. So you probably know this being called the Chebatarov density theorem, but some people, the Frobenius density theorem is a special case, so I just write that one instead. And we first have to fix the partition, lambda of n, and we're going to look at two densities and say that they're basically the same. So the density of primes p such that lambda p, so remember this is our degrees of irreducible factors, is equal to the specific lambda that we fixed. This is roughly the same as the density of elements in G, that's our Galois group, with cycle type lambda. Right, because we're a subgroup of Sn, everything has a cycle type, it's partition, and so we're basically saying that even if I don't know the Galois group, I can still pick a random element in the Galois group just by picking some random prime and factorizing modulo p. The caveat is that I don't actually get the element that I picked. I picked a random element, but I lose the information except for the cycle type. So I only know the cycle type of my element in the symmetric group. That's the same as knowing the conjugacy class. And so this is why I'm interested in invariable generation, because I don't actually know the element, but I do know its conjugacy class. So now we are ready to write an algorithm to tell us if we have Sn or not Sn. So our algorithm will take our polynomial and will give us yes or no. Basically all we have to do, basically describe it, is to pick random primes and then ask do elements with these conjugacy classes invariably generate Sn. So there's definitely some questions that people could ask here, so I'm going to leave those in case anybody wants those later. If the answer is yes, then we have successfully found a set of elements inside our Galois group which generate Sn. So the Galois group is certainly Sn. What if those elements do not invariably generate Sn? In this case, either we don't actually have the group Sn, or the group is Sn, but we managed to pick elements which don't invariably generate. So we can have a false negative. And the probability of that false negative, so the probability that we say no, but also the group is Sn, is just the probability that k random elements, so remember k is the number of primes I picked, so it's the probability that k random elements do not invariably generate Sn. Okay, so now what we want to do is give an estimate for this probability here. So let's give this a name so I don't have to keep writing so much. Let's call it Pi of G and K. It's going to be the probability that K random elements invariably generate G.
You mean do or don't? Because in the line above it was don't.
Yes, I mean do.
Okay,
And then I'm
okay,
gonna,
fine. That's fine, yeah.
Yeah. So I want this to be somehow big so that this, sorry, I forgot my pointer. I want this to be somehow big so that this is somehow small. And the results on this are relatively recent. So in 2015, we learned that there's some absolute constant, epsilon, which bounds the probability away from 0 for k equal to 4. Okay, what this actually means is that now our algorithm is proved to be, I think Alice called it a one-sided Monte Carlo algorithm. Because we get a false negative with a probability that we can somehow control, because basically we just need to know what the relationship between, you basically just do it a bunch of times until you get the probability that you want. So you pick 4 elements and then you pick 4 more and pick 4 more until you're satisfied that you have a certain level of accuracy. So, okay. And then a couple of years later, Eberhard, Ford, and Green showed that actually 4 is the best number you can get, because they show that in the limit, as n grows, the probability that 3 random elements invariably generate Sn tends to 0. So 3 elements are not good enough. So in this case, things look a bit different, because if we were working with generation and we cross this part out, then we would expect to see a 2 here and have it be going to 1. However, we actually can't even get close to 1. We can just get bounded away from 0 by some absolute constant. And you can actually prove that it's bounded away from 1 as well as bounded away from 0 for any fixed k here. Okay, so I think I should wrap up now, but I'm just going to briefly advertise what happens for general finite simple groups. So here I've written Sn, it's also true for An, they're the same in this case. And for the finite simple groups, you can also get some similar results. If you're going to fix the, if you're going to fix the rank and let Q go into infinity, then you can invariably generate with 2 elements with probability bounded away from 0. And the way that you prove this is just by using the same idea as before with the maximal subgroups, except now you're not looking at maximal subgroups, you're looking at unions of conjugates of maximal subgroups. And if you fix Q, but it has to be large, and you let n go to infinity, then you need 4 elements to bound your probability away from 0. And the way that we prove this is by a different technique completely, which is looking at, if you look at, for example, the special linear group as an algebraic group, then it has a Weil group. And Sn is the Weil group of SLN. And you use some cool algebraic stuff to make a connection between these elements and these elements, and you show that the result for SLN comes directly from the result for SN once you do some weird stuff with the elements. So instead of looking through maximal subgroups, you're just making some connections between elements in SLN, elements in SN, and you notice that they have similar patterns, and so they must have a similar probability of invariably generating. Yeah, okay, so thanks for listening. Any questions?